Will solar work at my property? In this lesson, we're going to start to begin to understand more about power and energy production, how the location of the solar array will affect the output of the system, variables like array tilt angle and orientation, weather patterns, shadows, what latitude that we live on the planet, and other things that can impact our system performance. We also want to start to discuss about roofs and roof types and some of the other data or things that need to be considered when we're planning a solar power system. When we start to look at solar energy production, solar begins to produce energy when the sun rises and stops when the sun sets. We can see this graph on the right-hand side that has power on the left of the graph and time of day on the bottom. When the sun rises in the morning, we're going to see as soon as the sun starts to hit the solar array, we'll produce a little bit of power. And as the sun becomes more intense and more direct on the surface of the array, the power goes up. And as the sun sets, the power goes down. That is a typical power curve with the output of a solar array on a typical sunny day. Now, we can have a lot of daily variations in our system as well. We can have things like clouds, and whether clouds are broken up all over or whether it's an overcast, hazy layer, could also be impacted by things like humidity in the air. Anything that's between the sun and the solar array is going to have an impact of energy production in some way or another. We see as the sun goes behind this cloud and we get a shadow, we see a dip in the output power from our solar array. And so we can start to imagine that, on a perfect clear day, we're going to create a normal output curve. But anytime we have things like clouds or haze or rain, we can have an impact on that and reduce the output of our system. So those are things that we start to plan on, and we plan that in a way by taking historical averages for weather data when we start to design systems. The other thing that impacts the output of our system is seasonal variations, which can basically be the sun's position in the sky, and how the sun's position in the sky varies with seasons will impact our performance. Here we see the winter path of the sun and the summer path of the sun at a given location. We can see based on the lower angle to the solar, we're going to have a little bit less intensity, and the power output in the winter can be a little bit lower. With the higher angle of the sun to the solar, we can get a higher power output. So in certain locations in the world, we can have a large difference in power and energy production based on the change in the seasons. So we need to understand what those differences are and how to account for them in our system designs. Now, if we're at a location that is more near to the equator, where we don't have a big variation in the summer path and the winter path of the sun, we could have a situation more like this, where the winter path and the summer path of the sun have relatively equivalent energy outputs. And throughout the year, near the equator, we may not get a large variation in energy output. Our monthly energy production may be, depending on other factors, very similar. Now, some of the other things that can impact, or what we can see with the impact based on our site location effects, is that the monthly energy production will depend on your latitude as well. Not only your latitude, but other things like the tilt angle of your array and the orientation and how that applies to the local area you live in your latitude. Just to understand and be clear, in the northern hemisphere, south-facing arrays provide the optimal power production. So when we live in the northern hemisphere, and the further north we go, the more important that array is to point to the south to have the most energy production. The closer we get towards the equator, south is still the better direction, but other things like east, west, and maybe even north might also produce good energy. So we need to evaluate that in every system design. It's going to be a little different for every site. depending on our latitude. So in the northern hemisphere, we basically want to point the array relatively towards the equator or towards the south in some way or another. And we can see in this graph here in a northern hemisphere location where we can have higher energy production in the summer months like May, June, July, and August, and lower energy production in the winter months like November, December, January, and February. Now, if we look at the graph on the right, if we're in the southern hemisphere, then in the southern hemisphere, north-facing arrays provide optimal production. So we're going to get basically a reverse here because of where the sun's at. And so in the southern hemisphere, we want to be pointing our arrays also towards the equator, which would be north or relatively north. And how close to the equator or how far away we are can make various impacts on our energy production. But being in the southern hemisphere, we're going to see more energy production in October, November, December, and January, for example, than we would in the May, June, July, August sort of months. So we can see how that's inverse based on what side of the planet we're on and how that can level out if we're along the equator and not have as much of an impact. Now, some of the other weather situations that can impact us other than just latitude is that monthly energy will depend on your local weather. On the left, we have a monsoon rainy season. So maybe we're near the equator, but we have variations month to month based on seasonal rain patterns. Some areas along the coast, we get regular fog that might change production throughout the season or throughout the day. And so any local weather patterns that are normal, that change the sun intensity that hits the array, we can have an impact on our energy production. In the graph on the right, we see snow season. So maybe we have decent production in the winter, but we got covered with snow. And if we're in areas that are higher elevation, either northern latitudes or high up in the mountains where we get snow, we need to account for that, not only in how to mount the array in order to reduce the amount of snow that accumulates on the solar, but also understand that the snow that sits on the array will have an impact in our monthly energy production, especially in those cold months. So some of the factors with our buildings that we need to consider. Factors to optimize the solar energy installation and the production. Well, I've mentioned a few of these already, but we'll go through them again. Array slope, meaning the tilt angle of the solar array. Array orientation really means, is it pointed south or east or west or north, and which direction is the array facing? How we mount the array can impact it. What sort of shading we have from trees, neighboring buildings, other parts of the house, anything that can impact the solar array from a shadow is going to have an impact in our power production. And then roof material as well won't necessarily have a energy production, but it will have an installation, possibly cost difference as well. So we need to consider all these sorts of things when we think about our site. Now, if we look at this situation again, and we see we have a winter path of the sun and a summer path of the sun, and we've added a couple of obstacles in here. We want to understand that shading on the array from neighboring objects differs based on time of year, depending on the height of the object, the distance from the solar array, and where we are latitude-wise can all impact how much a shadow either hits or doesn't hit, and how much of an energy impact we have from various shadows. So if we look at this winter path, we see we have a tree that in the winter, the tree is shading the array in the morning. So as soon as the sun comes up, we start to produce a little bit of power, but we're going to have a shadow on that array, which is going to impact our power production. As the sun begins to pass that obstacle and the array becomes in more full sun, we're going to start to ramp up our power production. And then when the sun fully clears the tree or the obstacle, so the shadow is gone altogether, then we're going to go up to full output, depending on the angle of the sun, how bright it is on the solar array. So we're going to see that shadow move, and we are going to see an output power variation because of that shadow. Shadows have a big impact on solar, and we need to understand how much the shading will impact our system production. And then, of course, the sun sets like a normal day. Now, if we look at the summer path of that sun, because the tree is the location it is and the path of the sun is different in the summer, we may not have an impact from that tree at all during summer months. And that shadow is going to be not as long, so it doesn't actually see the array. So we're going to have more of a normal production in the summer and an impact in the winter due to that tree shadow. Now, that allows our summer output power to ramp up as the sun gets over the array. But because we have this building to the west, we start to put a shadow in the afternoon from that building across our solar array, and we're going to immediately see a power impact. So we're going to see the output power from the solar drop off rapidly as the shadow from the neighboring building starts to sweep across the array during the afternoon. And so that's where we can get big variations in power production daily or monthly due to various shadows or obstructions that are going to be near or around our property. So when we design a system, we want to take into account, are we going to lose 10% or 20% or 40% due to shadows? Should we put the array in a different location? Maybe, because the impact from those shadows might be too great. That's something a good solar contractor will assess for you and determine whether this is a good location for solar, or maybe instead of the rooftop, it needs to go on the ground or a car park or some other location. So we minimize the shadow impact as much as possible. Now, when we consider array mounting, there's a lot of different ways we can attach to buildings and structures. So let's look at a couple of these here. Solar arrays can be mounted in different ways. And on the left-hand side, we see what we call flush racking, or a flush mounted system. What that means is we're attaching the solar array to the roof at the angle that the roof is at. And so we're using, because most of the time we are putting solar on existing buildings and we already have a roof. Those roofs weren't necessarily made for solar, but they might be the best location for solar from a cost and shade-free location. And so oftentimes, if we can, we want to use the roof we have and we want to put it at the angle we have, even if it's not a perfect angle. As solar becomes lower in cost, it allows us to do things where it maybe we lose a little bit of power, but it's worth it to use the roof we have. And so that's a flush mounted racking system on the left that is not elevated off the roof, just a few centimeters for air movement. In the middle, we have a flat racking system. So we have a lot of flat roofs around the world, and we can use various flat mounting structures that are designed to put solar arrays on flat roofs. Most of the time, these flat racking systems are going to have a low tilt angle to them, maybe a 5-degree or a 10-degree or possibly a 15-degree tilt angle. And because the rooftop is flat, we can choose the direction we want to point that array, whether it be south or east or west or north. We could select, a low angle system like that to go on any flat roofs. Those are very common for either flat roof residential systems or bigger commercial and industrial applications like we see here. One of the other things that I really like is this example on the right where we see an elevated racking system. Now, at this site, it's a great way that we can integrate the solar into the building and use it in a way to kind of dual purpose that particular location. By having an elevated rack structure above this flat roof, we're allowing this residential system to harness solar energy, but still utilize the roof space for families, for dinners, for meals, and for other rooftop space. So I love the dual purpose use of this. It's also similar to what we would do if we did like a car park system as well. Something where we do an elevated structure that can kind of make a dual use for an area, which is really great. And so there's a lot of ways that we can put solar in different locations, and there's a lot of different mounting systems available in the market today to help accommodate all these various roof mounting situations. Now, when we think about orientation, the roof azimuth affects the energy production of these flush-mounted PV systems. So roof azimuth really means the same as orientation, meaning east, south, west, north. A lot of times we'll look at that as a compass heading, and we say this array is facing south, which means 180 degrees on my compass, or I'm facing west at 270 degrees on my compass, or east at 90 degrees on my compass. So we think of that as kind of a direction as we face the array. As we discussed earlier, the latitude that we're at will impact how much power performance difference we have at these different orientations. So really, most of the time we can utilize the roof that we have in a lot of situations. And so our job is to take a look at the roof we have that's sunny and free from obstacles like shadows or too much equipment, and pick a roof that's going to work best. And then we can determine, based on the roof that we chose, how much energy production we'll actually get out of that location. Now, there's a few things that can vary when we look at these differing orientations, though. And so we have a difference in power and energy production when we change our array orientation. In this case, we're saying an east-facing solar array will produce more power in the morning. So as the sun comes up, the array is already facing to the east, and so we're going to get more intense sun first thing in the morning that's more direct to the surface of the solar array. So anytime we have a system that faces more to the east, we're going to see more morning production. Anytime we have an array that faces south, and now in this case we're assuming we're in a northern hemisphere, a south-facing solar array will produce more power during the middle of the day in the northern hemisphere. So that's our normal kind of output curve that we've looked at so far, assuming kind of middle of the day is our peak energy and our power production at the middle of the day. And then a west-facing array will produce more power in the afternoon, because when the sun rises, we really don't have much intense sun on that west array. And as the sun comes up to the middle of the day and heads off towards the late afternoon and end of day, that's when we're going to get the most sun intensity, and we're going to produce more power with a westerly facing array in the afternoon. Now, if we see these three graphs overlaid together, we have the morning, which is the east, the south, which is the kind of middle of the day, and the west array, which is the later in the afternoon curve. So this is also a reason why we see in a lot of roofs, maybe we use the east and the west roof if those are the best places we have, or if the roof is broken up into different surfaces, maybe sometimes it's all the roof areas. The closer you get to the equator, the less impact we have at these different directions. And so a good designer will assess how much energy production will come from each different array surface. And it's not uncommon to use the east, the south, the west, and the north potentially, depending on the same site. And so that just all needs to be assessed by the designer. All surfaces are good as long as they're free from shadows for the majority of the day. The other thing that'll impact our system performance and is part of our design is the array slope, or the angle. So the angle of the PV array affects the production of the system. If we look at the system on the left, we have a flat array, which is, we're saying in this case, truly flat. Flat array is not an optimal configuration due to the higher dirt accumulation that may require more washing or reduced energy production. And so that is like, let's say we're at the equator. In theory, a flat array is the best way to point it straight up. But what we find, if it's truly flat, and doesn't have any amount of tilt on it, that dirt and dust will accumulate on that glass surface, and then it will move to the edges and the corners slowly, maybe, and kind of pool over time, but not really blow off or rinse off very well when it rains. And so flat arrays just tend to be dirtier and either have a bigger power impact or require a lot more washing and maintenance to keep that flat array producing what it's supposed to. If I'm near the equator and I have a flat roof, I would rather put the array 5 or 10 degrees really in any direction, just to get dirt and dust to move off of it a little bit easier. Now, a low slope array, something that's a fairly low angle, is a good configuration for locations near the equator. Or if you're further from the equator, we can have increased summer production. The low angle means when the sun's higher overhead during the summer months, we get a greater summertime production. A steep slope roof, like we see on the right, is a good configuration for higher latitudes, so either way far, northern or southern latitudes, to point towards the equator more steeply in order to produce more energy. So this is a good configuration for higher latitude locations or increased winter production. So if we have a system that we're trying to produce more energy in the winter, we're going to point that array steeper like that in order to balance out that difference of summer and wintertime power production. This is just another look here at these different tilt angles and basically how they complement different seasons. So we see that the steep slope roof, and I know I've mentioned this before, but just to be clear, the more perpendicular or direct the sun is to the surface of the glass of the solar array, the more power that we get out of it. So that's why we see the tilt angle of the solar array and the location of the sun in the sky. Those two together tell us when we're going to produce more energy. So a steep slope array like this is going to produce more energy during winter. So more wintertime production because it's pointed more towards that low angle sun. Where on the right-hand side, that lower slope or lower tilt angle, that shallow tilt angle will produce more summer production because it's pointed more towards the high sky when the sun's high overhead. So that's why we see this difference in production, and we can either use the roof we have, or if we're designing a system from the beginning, we can choose tilt angles that might be more favorable for solar. So this is a orientation and tilt angle table. So tilt angle and orientation selection can help optimize PV production. What we're looking at here, this is just a sample, okay? So you can generate a table like this for any location, and this table is going to be based on, in this case we see here, a 34 degrees north latitude dry coastal climate location. So we just selected a location to show you an example here. Across the top we have tilt angle, so how steep is the roof? And on the left we have array orientation. Is it pointing south, southeast, southwest, east, west? We can work this out. This is obviously a north latitude one, so we didn't put a northern tilt on here, but that still could be good as well. So if we look at this example where we have the circle here, because of the latitude of 34 degrees north, we're saying that a 30-degree tilted solar array that is a little bit to the southwest is going to produce a 1, or basically what this means is 100% of our available power. Now, normally you would say that 30-degree orientation facing true south would be the highest output of the system, which it basically is. It's still 99%. The only reason there's little differences sometimes there in southeast or southwest in energy production would be because of local weather patterns. When we get into designing systems and utilizing some various programs and software modeling, we can model based on the location and historical weather patterns what amount of power and energy should be produced from our solar array given the latitude, longitude, local historical weather and the array tilt and orientation. So it can all be calculated. And what we see here is that whether we're at 18 degrees, 30 or 45 degrees, and anywhere, basically from southeast to southwest, we're getting like 90% or better of our output. It's really when we get off angle a long ways, like a full flat 90 tilt angle is going to lose quite a bit more power. The zero tilt angle is going to lose a bit of power. And so we can calculate this all out to figure out either where's the best or how much should I produce based on my given location. So another thing that impacts our system, one from a design perspective, also from a cost perspective, is the roof material itself. So most roof materials can accommodate rooftop PV installations. These are just some of the common rooftops that are out there. If we just run across these here in the upper corner, we have an asphalt shingle type of roof. Then we have a rounded concrete tile roof. So that's a concrete that is rounded. We have painted metal roofs we see all over the world as well. That comes in a lot of different colors and can be fastened in different ways. We also see corrugated metal roofs in a lot of places around the world. Flat concrete tile in the bottom left. So it's a concrete, but it's flat instead of round. The next one in the modified bitumen. We see that on flat commercial buildings a lot. It's a rolled out type of material that's often heated and then applied down to stick to itself. We have a tar and gravel where the tar makes up the waterproofing layer and then the gravel protects the tar from UV breakdown and things like that. And then on the right-hand side, we have a concrete flat roof that we see in a lot of places around the world as well. All of these different roof types have products on the market to attach to them. Every one of them is going to have a slightly different attachment point or connection to the roof, but there are major solar racking and mounting manufacturers all over the world that make products for all of these different applications. So part of the design is understanding what roof material do we have and what attachment product am I going to use in order to put my solar on this building, connect it to the roof, and make sure that it's going to be connected well enough to not blow away, meet our wind loads and our storm load designs based on our local area. Now, there are some difficult roofing materials out there too. Some roof materials can make it difficult to install rooftop PV. And by difficult, I usually just mean expensive. Of course you can attach to anything, but some things like the ones we see here, we may want to avoid them because of various issues with potential damage or additional solar costs. If we look through a few of these, in the upper left corner, we have what we call a stamped painted metal. Those are a big stamped piece that interlock. It's a very nice roof and it'll last a very long time. But they're really difficult to cut into and seal properly, and they're very difficult to walk on for installations because they crush very easily. Same with clay tile on the right. We see traditional clay tile in lots of places around the world, and it's a very beautiful roof, but it's very difficult to walk or maneuver around on. And when we get into removing tiles and anchoring in there, it can also be very difficult or costly. Similar to the slate roofs, some of these roofs will last forever if you don't touch them, but when we install solar, we need to anchor to something. And then wood roofs as well. They're just various types that are out there that can really cause additional problems when retrofitting solar into it. Now, all of these roofs, if we did solar as a new construction and used these types of roofs, integrating solar in the new construction process, these are a little bit easier to deal with. In a retrofit, these make for difficult or costly situations. A lot of times we've advised to remove that roof. So let's say we want to put the solar where the clay tile is. Maybe we remove all the clay tile and we put a different type of roof underneath it that's easier for us to waterproof. So there's ways around it, but these add costs compared to the other types that we just looked at. The other thing when we're evaluating our roof is we need to understand the structure. So your roof needs to be assessed to ensure it can withhold PV systems. We're thinking about the weight of the system. Now, overall, solar is not really that heavy, but that's where it comes down to what's the quality of construction, what's it designed for? Are those buildings designed for heavy wind and storm or hurricane or typhoon type of wind loads, or are they really light built because the area where you live doesn't have big storms normally? So the quality of the roof, the age of the building, and the weight loading the building can handle needs to be assessed before we put a lot of solar in. Most of the buildings out there in the world that are well built and relatively modern can accommodate the weight of solar. Because like I said, overall, the weight of the solar is not that big of an addition, but it always does need to be assessed to make sure we're not putting extra weight on a building that may be already compromised. Another thing we need to assess when we're looking at our site for solar is the equipment placement. We need to ensure the availability of space to store and place system components. Now, this is going to vary a lot, of course, because it's going to be different depending on the type of system. We've already talked about a lot of these different types of systems, being off-grid with energy storage or utility interactive and no battery. So sometimes if we're looking at things like a grid-connected system that's on a residence, we may have one small inverter. It doesn't take up a lot of room. It just needs a place on a wall to be hung. If we're looking at energy storage and battery systems, we're going to need a lot more space. Batteries take up a bigger space, may need to be ventilated to the outside depending on what type of batteries they are. Our inverters and our charge controllers and all that support equipment, depending on the size of the system. If it's small, we have smaller components, we can find better places to put it. If it's large systems, we need a big area sometimes to put all this equipment. Also thinking about things like, diesel generators and backup systems, or where those go and how these all go together. So space must be really considered. The other thing to think about, some of these inverters are designed to be outdoor rated and can handle the elements and the heat and the water and the snow and the cold. So some of them can do that. Some of them are designed to be indoors and need to be protected from those elements. And batteries as well need to be considered. Batteries don't like big temperature swings. And so all batteries are going to have a minimum and a maximum temperature range. Lithium-ion batteries can be a little even trickier. So some of this equipment may need to be inside conditioned space in order to keep it happy and keep that equipment alive. But we also want to think about things like bugs and critters and dust and anything that can get into this equipment. So the more we protect it, the longer that equipment's going to last. And the better it's going to perform for us. But we need to understand that there's a space requirement for this electrical equipment. And then one last thing to think about, if we are connecting to an existing building that has a utility connection, anytime we're either doing a grid connected or a backup power type of system on a building that's already existing, we need to ensure the availability of a grid connection point. So if it's a commercial or industrial building, we need to look at the switchgear that supplies the building and what sort of power either connection we have to that to either import or export energy in and out of the grid. So we need to look at the electrical switchgear and the services to find a location to tie in. We also need to understand the size of those services, what size the transformers that connect the building to the utility are, so we make sure we know what the limits are, how big of a system could we put on there. And then we need to look at things like circuit breaker locations, sizing of circuit breakers, and whether this is a commercial, industrial application or a residential application. All of these things are going to be limiting factors. We also need to understand the location of the meter and where we get to that point of connection, so we can try to get the rest of our new electrical system to meet with the existing electrical system in a way that works best for the site. Those are some of the considerations that we need to think about in these locations.